6 o'clock. Welcome to Global Technology TEC 5173. Say hi.
Hi.
Very good. Now, today we are in for a treat. Nice treat. Very good treat. We have Dr. Cheney, the Chair of School of Technology, speaking to us. And I want you, if you never met with Dr. Cheney, wave at me. Very good. So now I want us all to wave at him and say hi.
Hi.
Now, I want one of you to tell Dr. Cheney what do we mean by the hi in our class. It's not just say hi, we have something else. Anybody volunteer? What do we mean by say hi in class? We say it a lot in the class.
Stay involved.
Stay involved.
To be active.
This is a tradition we have in this class. While talking, I just surprise them and say hi. So if they are with me, not sleeping or thinking somewhere else, they will say hi right away. Say hi. Big one. Hi. Very good. Very good. So without much ado, I'll ask Dr. Cheney to kindly introduce himself to us and then tell us what he has on his heart and mind. Let's give him a hand, please.
Well, Dr. Wabi talked to me last week and asked me to invite me to come here and speak to you for a little bit. So I'll probably talk 20 or so minutes. But I'm looking at the course description online and just look at the first part of the course description. The course provides a dialogue on contemporary global problems influencing and influenced by technological advancements, and it goes on and so forth. So I took that into heart. I thought, okay, I want it to be technology related. And then I look at the qualification skills statement underneath there online as well. And the first part of that says open-mindedness with a free spirit of unbiased analysis of matters. So I thought I'll try to incorporate both of those things into the discussion today. So the first thing I want to do is this exercise. You all have various cards with statements on them. So I'd like you to turn those over now and take a look at those. And you see the sentence there. And I don't know, I'd like you to go through and count the number of letter F's in the statement. So why don't you take a minute and do that real quick. Count the number of letter F's. F.
Seven.
How many got one with 3 F's in it? Anybody? Okay, anybody have one with less than that? No, so 3. Why don't you trade yours? How many did you get? Oh, you aren't done yet? How many did you get? 7? Why don't you 2 trade? You had 3, you have one with 7. Trade your cards. And who else? Who else had 3? How many did you get? Anybody get something different than 3? How many? 8. Why don't you 2 trade? And count up the F's in each other's card. Who else? Who else said they had 3? 3. How many do you have?
4.
4. Why don't you 2 trade? Who else had 3? Anybody else have 3? What about 4? 4? How many do you have? 4? Well, how many do you have? 7. Why don't you 2 trade? You have 7? Trade with him. How many did you get?
7.
7? Anybody have anything other than 7 who hasn't traded yet?
I thought you said this. F is
What? 7F? You already traded, right? How many did you get this time? How many did you get?
I feel suddenly ready.
Yeah, I missed that one.
You get 3 still? You said there were 7 or 8 on there.
Let's get past that.
How many you get?
Yeah.
How many? 4? Why don't you two trade?
I totally missed one of those F's in
We think
scientific.
that's simple, right? You just count up the letters, right? How many people think that should be real simple? Everybody probably believes that should be real simple. Why are we getting different numbers of F's? Everybody has the same statement. I'll just clue you in on that
I
little
read
trick.
it 4
And
times.
right there it is.
Because of the baby word.
And there's 7. One of the things we learn when we're learning English, we learn phonetically. So the F is a V sound, a V sound. So all these ofs, you tend to miss them. Of. So a lot of times you're going to miss those Fs. And that's one of the things I want to try to get you to think about during today's discussion. And as you go through this course and on to your careers, it's very easy when you're trained to see things a certain way to miss things, okay? And I've got another exercise. How many of you in the research methods class tomorrow? Anybody in the research class?
Tuesday class.
Anybody tomorrow? I'll see you again tomorrow. I've got another exercise that's along the same lines that, you know, when you're programmed to think a certain way, you can miss the forest and the trees kind of thing. So that's the point of this exercise. To always be thinking about what you might be missing. And sometimes it's hard to do that. So I'm going to talk to you a little bit about what some companies have experienced because of what we call technological innovations. Does anybody know what an innovation is in technology? Give me an example of a technological innovation. Anybody? It's a technological innovation. What is that? What does that mean to you? What's your name? Ote. Ote. Ote? What's your what's a technological innovation to you?
Inventing new techniques.
New techniques? New ways of doing things?
Yes, new ways of doing things.
Okay. Anybody else? Technological innovation.
Something that makes a process easier.
Okay. Give me an example of a technological innovation. What do you got for me?
Hybrid cars.
Hybrid cars. So cars that, you know, they use different energy sources. Good example. Anybody else? Anyone? Technological innovation. Computers. The invention of computers. Did that change our society? Yeah, you bet it did. You bet it has. If you're older like we are, you would really appreciate how much it's changed society. If you grew up around computers, yeah, you've seen them get better all over the years, but you haven't seen the change. It went from no computers to computers. You know, it used to be reports and papers and all that had to be typed by hand. If you made mistakes, start over, you know. Very different world. So I'm going to talk to you a little bit about different types of innovations, and we actually can categorize different types of innovations. And there's 3 main categories that we generally talk about. A radical innovation, architectural innovation, and incremental innovation. I'm going to describe what each of those mean, give you some examples, and we'll talk about them a little bit. If you look at this diagram, have you seen a technology SCurve before? Anybody seen that before? It's very important for when you talk about, and by the way, I've been working hard today. I ripped my elbow out, so hard at work, coming in, guest lecturing, you know. Anyway, so technology SCurve describes how technologies evolve over time. It's very important for a person going into technological management or into the technological workforce to understand this. Because if you go to work for a firm and you're using some type of technology currently, and this technology follows this type of curve where, you know, changes in the technology are really rough in the beginning. They take a long time to develop the technology, and then it takes off. It hits a tipping point where it really takes off and starts to develop. And during this time, you have what's called incremental advancements in that technology. And so it's improving at a very rapid pace. Sales are high, everybody's making a lot of money, everybody in that industry is happy. And then at some point, it hits another tipping point where things start to slow down. And that particular technology can't really be advanced any further using the techniques that we currently use. So at some point, some new technologies are beginning to develop that usurps that previous technology and actually takes over, and now you have a new technology that's moving forward, and it goes through this rapid increase, incremental innovation increase, and then it begins to taper off, and you just have continuous S-curves that are representing the technology developments over time. So this linear portion would be where your incremental innovation's happening, these jumps to different technologies. That's when, you know, you've got some radical innovation that changes the way you do things. It may also be an architectural innovation, and I'll explain that a little bit. It may also cause this type of jump. But again, what's typically happening here, as the new technology comes out, you see it's actually performing below the existing technology, and that's because it's being developed. And it's not into a production level at that point. It's still in the lab. They're still trying to work out the bugs for this new technology, whatever it is, and then at some point it takes off and it takes over. And if you're a business that's working on this S-curve and you're not working in the new technology to develop it, what's going to happen? What's going to happen to your company if you're staying on this technology and not looking at the new technologies that are out there?
Won't grow.
What?
Won't grow.
You won't grow. What else is going to happen? When you get to this point and this new technology is better, what's going to happen to your company if you didn't
You're
invest
gonna
in
get
it?
outperformed. You're gonna get
Outperformed, and eventually you're going to go away. Okay? And I've got examples that I'm going to show you where it's happened historically. We'll talk about those. So this is again where, you know, we talk about this F exercise and it seems simple and kind of silly and it's fun and all that stuff. But that's really what happens here too at a larger scale. You get blinders on, you're focused on doing well and improving this technology, and you miss out on the new thing. And that, again, it happens at the individual level, it happens at the company level. So radical innovation, let's talk about that one first. So radical innovation is something where a new technical knowledge is required, okay? The way we operated in the past doesn't work anymore, or isn't satisfactory anymore. When we think about physics, for instance, just the technology, you know, knowledge of physics, and we worked on Newtonian physics, and then all of a sudden Einstein develops this new theory of relativity and changes the way we think about things. So this new knowledge is required to think about things from that new perspective. The existing knowledge oftentimes becomes obsolete. It doesn't matter anymore. What you knew about that old technology, not completely useless, but pretty close, okay? It's what you know about the new technology that matters. Firms have what we call core competencies. So a core competency is basically a firm has some knowledge base that they've developed over time. They've brought in people with technical knowledge, they grow and develop them, so they're very good at some particular technology. When a new technology comes into play, that core competency that they had with this old technology really doesn't help them much. And if they don't develop new competencies, they get left behind. And again, typically at least the replacement of the old technology, and often a firm, if they didn't invest in that new technology and develop in that new technology, goes away. I've got an example here. Who remembers VHS tapes, or who has some VHS tapes? Okay. They're pretty much hard to find anymore, aren't they? DVDs have replaced VHS tapes. Name another radical innovation you can think of. Anybody can think?
What about Kodak? How they didn't keep up with the digital?
Great example. That was actually one I wanted somebody to come up with that. That is awesome. I actually moved from New York in July. I lived about an hour south of Rochester. Kodak's in Rochester, New York. That's where their world headquarters is. And that company's in trouble. It's been in trouble for a long time. I think they're getting ready to file a second bankruptcy, or they have already, maybe. They were highly invested in film. Okay, they were the best in the world, right? Right? Wouldn't she say? Widely recognized. And then the digital cameras took over, and they just kind of got left behind.
And one question I may ask here, since you mentioned Kodak. I read that the digital photography was started at Kodak.
Yeah, they
So
actually
it's
had the
amazing.
technology.
So it's not like somebody
That's
else.
absolutely true.
How come that they start digital and they go bankrupt? I mean,
Again, they didn't see the big picture, I guess, you know? I mean,
it's amazing.
that happens a lot of times too. You see that in a lot of different scenarios where the big company, the established firm,
Started something.
develops some technology maybe that somebody else develops and takes it to the next level and they get left behind. They just didn't see the future. So again, count the number of F's. Okay? Any other comments about radical innovations? Very good. Architectural innovations is a little bit different. In architectural innovation, you aren't really changing components. You may be changing the configuration of things so the process works better or differently than it did in the past. And the example I have of that is a little complicated. I'm not going to get too in-depth with this. I do want to share a little bit with you. If you want to read more about it, I'm going to show you the paper. It's by Henderson and Clark, 1990 publication. They did research on the semiconductor photolithographic, that's a mouthful, photolithographic alignment equipment. And basically this is a silicon wafer. If you haven't seen one, it looks kind of like a DVD almost, okay? They're about the same size generally. And you can see on here, every one of these little rectangles is a circuit. Very tiny, complicated circuit. And this is a little magnified view here on the right. You can see some larger pictures of those circuits. In each one of these, you know, there's a very complicated pattern of circuit here. This is all our modern electronics operate, okay, on these microcircuits. And what I'm going to do, I'm going to get out of this and go to this paper. Remember, we're talking about architectural innovations. Lithographic process works. So you've got that wafer that I showed you pictures of the wafer with the circuit on it. Well, this is the wafer of silicon. It's made out of silicon, and it doesn't have anything on it yet, okay? So the way the process works is you have what's called a resist, and it's a photoactive type of material. So you have a mask that goes over that. Now the mask is in the shape or the pattern that you're going to have the circuit in. So the mask is basically the shape of the circuit, what the circuit will look like. And again, it's very tiny, very intricate. And that mask is put over top of the resist, and light is shown through the gaps, which cures this resist in those areas where the light showed through. So now the area that's not covered with resist anymore can be covered with deposited material so that the circuit can be made. So basically that deposited material then, because the resist is preventing it from attaching in those areas where the light got exposed to the resist, those areas now, this deposited material can't set on, and that metal then is forming the circuit in all those locations. Okay? Then the resist that's been cured is taken off, and now you have a wafer with these circuits on it. Okay? Again, we're looking at a cross-sectional view. If you flip it this way, you'd see that wafer with the circuits that I showed you earlier. Now the way this worked originally, they have an alignment system, and it's again a very small scale here, very fine. You've got this alignment system that holds the mask in place. Okay, as it comes down, it holds it in place. Well, what happens is because that mask is in contact with the resist material, you can see up here in this picture, the mask is actually in contact with the resist. So it end up getting, the mask gets damaged very easily in that process. So then it's very expensive to replace the mask and all those things. And so the architectural innovation that came up was to set an alignment system whereby the mask would actually not touch the wafer. So the light would shine through here, and the light would come through, and actually the light would disperse a little bit when it reached the edge of the mask. So you maybe wouldn't get as much precision with the process. So maybe now, instead of 10 microns, you have 9.5 microns of precision. So your precision isn't as good with that process. But what they found was, because they kept things out of contact with each other, it would last longer, they wouldn't damage materials, and so productivity would increase. Okay, so they could actually get more throughput in the system by having this different alignment system that actually didn't make actual physical contact. So we call that a proximity alignment. And then they had a number of other architectural type innovations. And when I say, again, architectural, we're not really changing the basic process here. It's still, you've got the mask, you shine light through it, you cures things. The process is still essentially the same. It's this alignment system that's modified over time. So the technology really hasn't changed. It's how we apply and implement that technology, how we arrange the technology. And this is, again, more focused on process, but there are other examples in product as well. So this is a summary table right here that talks about the different types of aligners. So you got proximity aligner, then this scanning projection, first generation stepper. So these are different approaches to producing the same type of wafer. So again, the technology really hasn't changed. It's how we're organizing it. And you see what happened here. This is a list of different companies. We start with contact lithography that I showed you first, where they're touching each other, then proximity. And what happened to this company, Cobuilt? 44% of the market, down to 8, or actually to 0, and they just disappeared. So they, had the majority of the market when you had this type of architecture. When you switched architecture, even though they invested in the equipment, they didn't have the core competency to work with that equipment, and they went away. So then you got Canon takes over. So you go to this proximity type alignment system, Canon takes the market. Then what happens? You go to scanners, PerkinElmer takes the market. Go to steppers, you got a new market entrant. And then step and repeat, Nikon takes the market. You can see how the architectural innovation, even though these companies invested in the technologies, like Dr. Wabi mentioned about Kodak, they developed digital photography. Where are they now? That's what happened to these companies. Any questions on architectural? Again, I just want you to understand the concept. I don't want to turn you into stereolithography people unless you really want to do that. I suppose somebody does. Somebody has to want to do it, right? Okay. Questions on architectural? So we got radical, huge technological change, revolutionizes the market, architectural innovations, and the last type, and probably in many ways the most important, incremental innovation. Or in the manufacturing world, you might hear the term Kaizen, if you haven't heard that before. Continuous improvement, essentially, is what that means. Incremental improvement. And basically, you're building on existing knowledge. You're improving the current state of knowledge in that technology. Good example of that is with computers. I understand you're supposed to be talking about computers in the world this week or something. So this fits right in. You look at computers over the last 10 years. Have there been any major changes in the technology? Processing speeds improved. The storage capacity, RAM, so you can open up more files and more complicated software. But really, the core root idea of the computer hasn't changed much over the last 10, 20 years. Maybe more. I'm getting older. Maybe it's over 20 now. So that's a good example of incremental innovation. What else? Anybody got any other thoughts on incremental? Can you think of one in incremental innovation?
Cars?
Okay, what about it? What's incremental innovation?
Well, I mean, they just kind of get a little bit different, a little bit better.
Gas mileage?
You know, right,
Gas
exactly.
mileage is, they've made vehicles that are better gas mileage. There's an example.
Safety aside.
Safety, airbags, okay. I got a whole nother discussion on those things, but, well, I'm gonna sidetrack a little bit and get away from my planned lecture, but, you look at these new technologies, and what do you see, what have you seen happen over the last 10 years with the new technology that comes out? Like interlock brake systems. Who remembers when they first came out with those? Anybody? See, I'm older, see? I don't mean to say that in a mean way, just more experienced. Interlock brakes, what company came out with them first?
I have no idea.
Most of those innovations like that, you see come out on the real high-end vehicles at first, don't you? And they're real expensive, and oh, this is the thing that separates us from the competition. Well, we got analog brakes now. And if you remember the analog brakes when they first came out, it was gung, 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 real slow repetition. Now they're like, they really work well. But when they first came out, it was a big deal. Oh, this has analog brakes, but it's the $50,000 vehicles that have them. And now every car pretty much has them. Okay? So what happens is, in the beginning, that new technology is a differentiator. It separates you from the pack. And then over time, now you got to come up with some new differentiator. Something new that you do differently than the other competition to separate out and say, this is why you should pay $60,000 for our vehicle. Because we have this technology. So over time, those technologies diminish and become the norm. That's what you find happening. Kind of a sidetrack. But anyway, I'm going to focus a little bit on incremental innovation. I'm running longer than I expected, so I'll try to zip through this. Again, I'm not expecting you to know remember this stuff long term necessarily, unless you're interested in it. But if you look at manufacturing performance, we look at things like speed, quality, dependability, cost, flexibility, and how do we improve those things over time? Let me just go to, so we look at some different improvement methods. Plan, do, check, act is more of a management cycle. So you plan something out, you do it, you check and see how it did, what improvements can be made, and then you act and make improvements, and you go through the cycle again. So it's kind of a cyclical way of thinking about continual improvement. And again, it can be applied in just about everything you do. Another one is the 5 why process. So give me a problem that you have. Anybody? Who has a problem? Who has a problem they want to share with me?
Technological problem?
Anybody? Wow.
All problems are solved.
High class. Give me a problem you're having, Dr. Wabi. Don't be shy.
Well, a technological problem, maybe the internet being slower sometimes.
Okay, the internet's slow. Why?
Why?
Why is the internet slow?
Well, that's a good question.
So it's a root cause method. Let me give you an example we can walk through. Okay, my back hurts.
Why?
Oh, I'm glad you asked. Well, my back hurts because I haven't been exercising.
Why?
Why? Well, I don't have time to exercise because it's not a priority. Oh, well, now we're getting closer to the root cause. So you kind of see how the process works? So it's a way of, being deliberate about trying to find what the real cause of the issue is. You can start to begin to address it, because until you get, drilled down to that root cause, it's hard to solve the problem. It's like putting a Band-Aid on, something where the Band-Aid isn't going to be effective. There's a deeper issue. Okay, I'll skip over that. We'll go to the next slide. So I'll talk briefly about some tools of problem solving, and then we'll wrap things up. So these are some different, again, tools that are used for incremental innovation, solving issues day to day to try to make things better, improve processes, improve operations, and so forth. So these are some different tools that you may find useful for that type of activity. So I'm going to talk briefly about each of those. A check sheet is just a tally sheet. You know, if you want to find out, you know, this is looking at traffic. How did people find out about something? Did they look at newspapers, daily ads, weekly ads, websites, road signs, or referrals? How did they find out about something? So you track that and tally it up. 7 people on this day, 4 on this day, and so forth. So it's just a simple check sheet, a way to tally information so that you can look at it then, and very quickly you can see what's the best approach to use. There's a couple that are much higher than the others. What are they? What are the most effective ways that they're getting information out to customers?
Website.
Yeah, the website and daily newspaper ads. And you can turn that, flip that upside down and create what's called a histogram. That's another tool. And it's basically taking those counts and, you know, spreading them out. You know, where did the most occur? And looking how that spreads over time. So like you could take a measurement of something you're producing and, you know, measure that device. Let's say you're measuring the width of something, and somewhere it's supposed to be about an inch, and you're measuring it, and you get various measurements. So maybe this is exactly 1 inch, and then these are spread out from that. So 1.1 inch is over here, 0.9 inch, and so forth. Just an example. So you're taking counts and you're plotting that data, and you're trying to see how much variability there is in something. So you've got a measurement. How much spread is there in that measurement? Are you between 0.9 and 1.1 inches? Are you between 0.99 and 1.01? You know, how fine is that? How tight is that measurement? How precise? And how accurate? You know, if this most common measurement is 2 inches and you're shooting for 1, what does that tell you? It's really far off, right? So that's the histogram. Again, it's just a quick method, plot data and see what you've got. Another way to do root cause analysis, if you're trying to identify, let's say I've got a process operation and I'm making something and I'm getting defective parts, defective product. And I track over time and see, you know, which things in that product have issues. Are they fasteners, connections, interface and protection, the main part, structural components, labels? Where am I having defects occur? And so I can count that up, I can track it with the Pareto chart, and essentially I'm just counting up the number of times that defect appeared when I made my product. And you might have some products that have multiple things, so you count them in multiple columns. Another way to do that, rather than counting up the number of failures, if you look here, look at structural down here. I only had 24 structural failures, so it's not a big issue, right? I shouldn't worry about that. What should I worry about according to this chart? What's my biggest concern? That's where I'm going to get the best bang for the buck. If I address the fasteners and get that right, boy, you know, I've cut way back on the number of defects, haven't I? But you can also look at that from a cost perspective. How much did those 24 structural defects cost me? Oh, whoa, whoa. Hold on, now I've got a flipped issue, okay? You know, before, what was the connectors? Fasteners, right? Fasteners was number 1, now where's it at? It really doesn't cost me much money to have that kind of defect. So I'm not going to be concerned about that. I'm going to address the one that's costing me the most. If I can fix those 24 structural defects, I can cut my, you know, cost of failed components down in half. Okay? So that's the Pareto chart. It's another tool that we use for continuous improvement. If you have any questions on these, if I'm going too fast, yeah, I'm not trying to turn you into experts necessarily. I'm just trying to give you some tools that are out there. If you want to look more into these, they're very easy to find on the web. So you can find out more detail about them and practice using them, integrate them into papers that you're writing. Now the next one's scatter diagram, and this is just looking at relationship between two variables like temperature and viscosity of a liquid. Might be one example. So is there a positive correlation? When one goes up, the other goes up too? And is it linear? So when this doubles also? So that's a positive linear relationship. It's a very strong one because you don't see a lot of scatter. Okay, we're over here, you have a moderate positive relationship, and we say that's moderate because it's not really, if you fit a straight line through that data, you're going to have a lot of points that are further away from that line. Whereas over here, fit a straight line through that data, most of the points are going to be pretty close to that line. So moderate positive relationship. If you look at the relationship here, you got data scattered all over the place. There's not really any correlation between the two. So when one goes up, the other might go up or it might go down, you just don't know. So there's no relationship between the two variables. You can have a negative relationship, and again, moderate or strong, depending on the scatter. And then another possibility might be there's not, maybe in the beginning when one's going up, this is going down, and then at some point it hits a tipping point, and it actually starts increasing as the other increases. So getting an idea of how two variables are related can help you to solve problems. Let's say you've got a machine with multiple settings on it. You've got a setting for pressure, temperature, humidity, those three, let's say. And now you want to see how those three variables relate to each other. Again, knowing how they relate can help you to get the right settings to produce a problem. So that's where the scatter diagram, looking at relationships of variables, can come into play in a manufacturing or production type setting. Process flow charts, if you're trying to look at a process and see how it's operating, this is used a lot in computer programming. It's also used in manufacturing. And what you're trying to do here is identify how you can make the process move more smoothly, trying to eliminate waste in a process. That's where the process flow charts are used. The next one is a root cause analysis approach. I shared one with you earlier. What was it? Root cause, what did we do? My back hurting, 5Y, okay. This is called the Ishikawa diagram. It's also called the cause and effect diagram. It's also called the fishbone diagram, and it basically looks like this. Let me draw a picture over here. This is a horrible pen. How many good pens? Where's a good pen? Oh, that's much better. So the reason it's called a fishbone diagram is because it kind of looks like a fishbone. So you've got some problem here on the right. Okay, again, Ishikawa, cause and effect, and fishbone diagram are all the same thing, just different words that are used for it. So you're essentially trying to identify the root cause of this problem. So you identify major areas, okay, and you can see those here for this particular case, and that's not locked in, those can vary by the problem. But you identify main areas, and then you identify sub-areas within those. So, maybe you don't have the right people in the company. Maybe you need to hire some new help. Maybe your management is disorganized or they treat people bad. So there could be issues that way. Maybe the equipment's old. So you're identifying potential problems, and then through this you line up, find out, okay, what's causing the problem, and then the group that has the most knowledge about the process of the people and the problem, the organization, looks at that and figures out what are the main areas that we need to fix to try to correct this problem. So it's again a systematic way of drilling down and finding out what the root causes are. The last one, just a run diagram, that's to try to see how a process or something is done over time. Maybe it's a measurement, maybe it's, again, trying to see, in this particular example, you've got a registration time at a doctor's office. So you're looking at the amount of time it takes versus the day. So some days it's performing well, some days it's not performing well. Some days it takes a long time to register patients. Okay? So this is just one example. Again, it could be a variable, a measurement that you track over time. So you randomly take a a shaft that you're producing and you measure it, and you take that measurement and then you plot it over time. And you're seeing how that variable is performing. You're looking for lots of scatter, you're looking for trends. You know, let's say you've got a shaft that you're producing and the diameter keeps going up slowly, but it's creeping up over time. What might that be something? What might that indicate? If your diameter, you're trying to produce a 1-inch diameter shaft and over time it just keeps creeping up. Maybe it's 1.1 after a month. What does that mean? What might be causing that?
Die might be getting worn or something.
Die worn, tool wear, yep, very good. So again, getting an idea of what a variable is doing over time, how you're performing over time. You know, if you've got certain days where certain staff are in here on these days when you're not performing as well, maybe there's some retraining that you need to do, you know, to help those people to perform better. Intermix them with the people that are performing well so you get some cross-training to happen and bring those highs down so you're performing more consistently. So again, a way to help identify the issues and solve problems. So those are just some tools, again, used for incremental innovation. So what did we talk about? We talked about 3 types of innovation. Radical innovation, what's the example of that? DVDs from VHS. Kodak we talked about. Architectural innovation.
Semiconductor.
We talked about the lithographic process. You're not really changing the core technology, just reconfiguring some things in that process to make it improve. And sometimes we saw the data, companies get left behind in that process, don't they? Again, trying to adapt your core competencies as a company so that you can work well with the new innovations. And then finally, the incremental innovation, continuous improvement, trying to improve over time. And here you see those S-curves, new technology, incremental innovation, radical innovation. Or it could be architectural too. Okay? Questions on the S-curve? So, in closing, be open-minded, be a continuous learner. Those are important things. That's what we hope people get out of college and they become continuous learners. They don't stop learning. I sure hope I don't. I don't think I have. And this finished files is a good example for you to remember that. Silly thing, but it makes a strong point. Any questions?
Any questions?
You did very well.
I appreciate the opportunity to come and talk to you.
Got very well.
If you ever need anything, downstairs.
Room 1010.
1018 actually is my room, but
One in-
yeah, in the office complex down there. If you need anything, let me know.
You say your name was?
Austin Cheney. Cheney.
Chair of the School of Technology. Because when we arrived at the first, we had affiliation. Okay, so please join with me in thanking Dr. Cheney.
Thank you. I appreciate the opportunity.